last lecture on the air pollution module is about acid deposition. So we've talked a lot about the chemistry and the species, the air pollution species in the atmosphere, but eventually they have to go away. And with pollutants, the main way that they go away is by being deposited on the Earth's surface. And this can be through dry deposition, so just as dust particles or gas molecules, but it also can be through wet deposition, which is rain. So today we're going to focus on the history and what exactly acid rain and acid deposition is. So we've known about acid rain for a long time. A citizen scientist, a pharmacist who lived in Manchester, England, which is a city there, measured the pH of rain in Manchester and then compared it to the pH of rain on the coast. And the coast presumably is somewhere with fewer human activities, not as much of a population the way the city was and no industrial activities. And he noticed that it was more acidic in Manchester. And it's interesting to think, when do you think this would have been? When was this first identified? And I'm always surprised to find out that it was actually in the 19th century. So in the 1800s, we've known about this acidity of rain from human activities for a long time. But it was essentially ignored until the 1950s. And what started being noticed in the 1950s was that there were large declines in fish populations across European lakes, some really massive dead zones in these lakes, because of the acidity of rain. And so acid rain wasn't considered an environmental issue until the impacts started to be really visible and basically that you couldn't ignore them anymore. So if we talk about the chemical composition of rain, pure water has a pH of 7, but of course rainwater will always have stuff in it in addition to just water because of the composition of the atmosphere. And this has nothing to do with human activities. This is true long before humans started putting pollutants in the atmosphere. And the main thing that impacts water, the pH of water naturally, is that rain equilibrates with CO2. So carbon dioxide has a pre-industrial concentration of 280 ppm, and it's a weak acid. So it dissociates to form bicarbonate, which is this species here, and then dissociates further to form carbonate, which is this species here. So based on the equilibrium constants of these reactions, and the fact that the pre-industrial CO2 concentration was 280 ppm, you can calculate that rain then would have a pH of 5.7, which is naturally a little bit acidic. But of course, there's other naturally occurring acids and bases in addition to CO2. So you have nitric acid from NOx oxidation. We've talked about NOx. So before human activities, you'd have NOx from lightning and soil emissions. You also have organic acids, and these would come from the biosphere, so things that would be released from plants and trees. You'd have sulfuric acid from SO2 oxidation, and SO2 has natural sources from the biosphere, primarily volcanoes. And these acids would be balanced by naturally occurring bases. The main one being ammonium from ammonia emissions, and ammonia can be emitted naturally from vegetation and different aspects of the biosphere. And there's also calcium carbonate, in suspended soil dust, where the calcium and things like that act as a natural base. So if you include all of those things together, it gives you a natural range of a pH of about 5 to 7 for rainwater, depending on where you are and the balance of these different emissions. So the technical definition for acid rain is not necessarily that the rain is acidic. The technical definition of acid rain is rain with a pH of less than 5. Okay, so that's what acid rain is considered. So it's acidic below the range of the natural variation. And just a quick pH refresher, so the pH of 7 is neutral. So technically anything less than 7 is acidic. So that natural range of 5 to 7 means rain is naturally acidic. But it's anything less than 5 that's technically acid rain. pH of greater than 7 is considered basic. And remember, the pH is the negative log of the H plus concentration. And the fact that it's a log scale means small changes in pH are actually large changes in the H plus concentration. And the more H plus means the more acidic. So a solution with an H plus concentration or with a pH of 1 is 100 times higher in concentration of H plus than a solution with a pH of 3. Okay, so that's because of the log scale. You have to sort of keep that in mind. So if we look at the chemical composition of rain locally in South Africa, I'm pulling this from a study that was done in the Highveld. You can see, and in the Vaal Triangle, this is from 4 different locations where the pH of rain was monitored and the chemical composition of the rain was monitored over time. And the Vall Triangle Station is considered the most polluted site. It's highly industrialized, has a very high population density. And we can compare its composition to this Louis Tricard site, which is the most rural. So this is 500 kilometers away from Johannesburg. It's more agricultural, more arid. It's more of a background site. So it's nice to contrast with the Vall Triangle. And you can see the composition of sulfates. The concentration of sulfates is much higher in the Vall Triangle from SO2 emissions. Nitrate is much higher in concentration from NOx emissions. And there's a little bit more chloride ions. And so the H plus concentration is much higher as a result of these acidic species. There's also more ammonium, which is interesting in the Vall Triangle than the Vall Tricard, and more calcium, more magnesium, more potassium, more sodium. So there's, in general, more stuff, for sure, as you compare these. And so what does this mean? Well, a couple of things to notice. The H plus is the dominant cation, and it's balanced by sulfate and nitrate, the dominant anions. And of course, there's some alkaline soil dust contribution. But in this case, sulfuric acid and nitric acid are the main contributors to rain acidity. And this is true in most parts of the world because SO2 and NOx tend to be your main pollutants. And so nitric acid and H2SO4 dissociate in water and they produce this H+. And you can see sulfate's actually a stronger acid because it's producing 2 H+. And it's this H+, remember the pH is the negative log of the H+ concentration. So if you have more H+, you're going to have a lower pH, which is going to give you your increased acidity. So this, of course, the H+, is less than the sum of the anions, and that's because the bases are neutralizing the acidity. So there's some ammonium, calcium, and sodium to neutralize this acidity, and that's really important. So if you have a region with the right kind of alkaline soil dust with enough sort of ammonium, calcium, sodium around, then even with high acidic emissions, you aren't going to have as bad of an acid rain problem. So acid rain is about the emissions of acidic species, but it's also about the receiving environment, so the type of soil you have around. And just a sort of little note on what we're looking at here in terms of the chemical composition. You see the units over here are in something called microequivalents per liter. And that's a little bit different than typical units for concentration. And it's because this includes the charge of the molecule. So nitrate, 1 mole per liter, is equal to 1 equivalent per liter of nitrate. And that's because nitrate has a charge of -1. So it's NO3 minus. Whereas sulfate, 1 mole per liter of sulfate is actually equal to 2 equivalents per liter of sulfate. And that's because sulfate has a charge of -2. And this is important because the sulfate charge of -2 led there to be 2 H+ molecules, whereas the nitrate led to 1 H+ molecule. So this is accounting for that when you look at concentrations in microequivalents per liter. Okay, so where are these acids coming from? And essentially they're coming from the main sources of NOx and SO2. So previously in lecture 2, we talked about the formation of NOx and how the way to get rid of NOx was to form nitric acid. So this was the daytime loss process for NOx, was that it formed nitric acid. And during the nighttime loss process of NOx, you also form nitric acid. Okay, so this is how you're getting from emissions of nitrogen oxides, and we talked about the chemistry and what NOx does and forms ozone. But as NOx is removed, so it's good that it's removed because it stops forming ozone, but it leads to this additional problem, which is the formation of nitric acid that contributes significantly to acid rain. We haven't talked much about SO2 in any of the previous lectures because we were focused on NOx as a precursor to ozone. But SO2 is also a large global pollutant. Here is a little breakdown of SO2 emissions as a function of main sectors, and then there's a time component across the table. So you can see, if we look at 1990, the main emissions were from the energy sector, followed by industry, and then a little bit from residential and transport. And if we look over time, SO2 emissions have declined nicely, and that's actually because of acid rain. When acid rain was recognized as such a problem, because sulfate has that ability to form two H pluses, it was the SO2 that was identified as the main culprit for acid rain. And so there's been a lot of policies globally to reduce the emissions of SO2. And you can see, especially from the energy sector, that number has gone down nicely from 1990 to 2011. The residential number has gone down. So, well, let's talk. Why has the energy sector number gone down? Well, it's required now in most places when you burn coal that has a high sulfur content, you have to have some technology to reduce the SO2 emissions from the coal-fired power plant. In the residential sector, this has come from switching people from domestic burning of things like coal and biomass to electricity, so cleaner electricity. Industry, there's actually been an increase, and that is also partly because there's such a thing as high sulfur coal, and as the energy sector was no longer allowed to emit SO2, that high sulfur coal got pumped to the industrial sector. Transport, it's gone down quite a bit, and again, that's due to refining fuels. Whereas shipping, it's gone up. And this is also in direct contrast. These are sort of connected in the same way that these are connected, in that as you could no longer burn high sulfur fuels for transport, they got dumped over to international shipping. This happens a lot with international shipping as well as aviation, because it's a lot harder to regulate international shipping because it's not clear which country's air quality policies they should have to adhere to. And so there tends to be a lot of dirty fuels in international shipping. This is a look at SO2 emissions globally. So you can see here, this is hotspots in terms of gigagrams of SO2 per year per grid cell, with darker colors being more SO2 emissions. It's not that different from NOx emissions. You can see high values in the eastern part of the US, where most of the coal-fired power plants are. A lot in China. China also tends to have high sulfur coal, but a lot of fossil fuel emissions. India is a hotspot here. Europe's quite high. You can see the South African Highveld is quite high here as well. And these are actually from 2010 model emissions. So this is a global modeling study, which is why you can see there's tends to be focused on where we have a good idea of what the emissions are. So places that are doing emissions inventories. Here, this is another way of looking at SO2 emissions on the left, globally by primary source. So you can see, if we go back to the pre-industrial around 1850, there would have been a little bit of open burning and anthropogenic industrial activities. So both of those are pretty evenly split. This dark sort of weird brown color shows you the strong increase in coal use over time. And then a pickup in petroleum combustion, things like industrial activities, metal smelting are represented here, waste burning, etc. There's a couple of interesting things you can see here because this is so driven by energy and industry. You can see nicely just about here, I would say, is the Great Depression. You can see that a lot of industries slowed down. You can see another dip here and here. These are the world wars. And then you can see also this nice sharp rise just after the World War. That's the post-war economic expansion. 1950 to 1970, this is basically your post-war massive boom. That's where you have the largest per decade growth. And there's some declines in this same time period in US and Europe coal combustion, but there's also an increase in Chinese coal combustion. And then right around here in the 80s, we get the fall of the Soviet Union, and you can see that also very nicely. On the right-hand side is a different look at global SO2 emissions. Here you're looking at end-use sector. So what was all of this used for? And so you can see energy combustion, industry, smelting, transport, domestic uses, shipping. It's just a slightly different way of looking at the emissions. Here they're broken down more by region. And so this is where you can start to see the sort of slight declines in North America and Europe here, while East Asia and China continues to grow. SO2 emissions tend to increase in proportion to activity levels until about 1970. So I would say around here, technology started to improve. So you could have more and more industrial activity, but lower and lower emissions as a result of changes in technology. There also was a switch here to lower sulfur coal, particularly in the US and Europe. So it's not necessarily that less coal was being burned, it was just coal with less sulfur. And the main technology that was introduced around the 70s is what's called flue gas desulfurization. And that's used in a lot of different places. So this is a look at SO2 emissions in South Africa. So this is from a South African emissions inventory. And this is from two different estimates. You can see they sort of overlap nicely in the mid-2000s. Globally, South Africa's SO2 emissions are considered to be fairly small, but you can see they actually map fairly well with GDP. You can see the sort of late 90s economic growth that occurs, bit of recession through here, and continued growth. Okay, so lots about SO2 emissions, but how do we actually go from SO2 to sulfuric acid? So like most things I've introduced you guys to, SO2 is oxidized by the OH radical, which is our big oxidant. It reacts with one of these inert bodies, that's your M here. Goes on to react with O2. These are very quick reactions, eventually reacting with water to form H2SO4. The lifetime of SO2 against this process is about 1 to 2 weeks, which means that this actually takes a long time. And that gives a lot of time for SO2 to be transported. So you'd expect if you had a large regional source of SO2, it would actually spread for a long time. And this is all gas phase chemistry. But we know that this doesn't make sense, and that's because the sulfate concentrations in rain tend to be really high, very close to where the SO2 source regions are. And so it doesn't make sense that it should be living for 1 to 2 weeks, or you'd expect it to be really spread out. And so what was discovered when people were investigating this acid rain problem and trying to figure out why you weren't seeing it as far away from the source as you should, is that in this case, most of the oxidation of SO2 actually takes place in cloud and rain droplets. So it's not as OH driven as a lot of the other atmospheric chemistry is. And so what happens is the SO2 gas dissolves into a rain or cloud droplet, which is denoted by this process here. And then it reacts with hydrogen peroxide to form sulfate. And so this is what it's called. It's actually an acid catalyzed process. And so this is the first time in these lectures on air pollution that we've explicitly talked about aqueous chemistry. So moving away from gas phase chemistry in the atmosphere to chemistry that happens in the cloud and rain droplets. And so if you have high emissions of SO2, you end up having high deposition of sulfuric acid. And these emission and deposition units are the same. And the only thing you need to know to understand how much of the emissions end up in deposition is some sort of a deposition rate. So how much is it raining per day? And that's the sort of basic meteorological information you can get anywhere, right? So you have emissions of SO2 in teragrams per year, and then you have deposition units that are essentially the same, teragrams per year. And you just need to know this, how much is it raining in a given place? Okay. So back to what I introduced you guys to, the study of rain in South Africa from these 4 different sites. We have the most polluted here. We looked at some concentrations, and the least polluted. But there's also Skukuza, which is sort of a balance of a little bit polluted and a little bit not. And then this other highly polluted site. And so here you can see these are histograms showing the frequency of rain events with pH in these various ranges. And so we can start with the Vol Triangle, which is the most polluted, and you see the most frequent pH of rain is in the 4.2 to 4.4 range. So that falls within the fairly quite acidic, so that's officially acid rain. I should mention this is from every rain event was collected from 2009 to 2014. So there's a lot of rain events accounted for. So this is from essentially this vol triangle. These values are driven by high NOx and SO2 emissions in Mpumalanga from coal-fired power plants. And then if you look at the other slightly polluted site, which would be this one here, you can see again, your two most frequent events are in the 4 to 4.4. So again, that's considered officially acid rain. Anything basically below this value is considered acid rain. You can say the same here. And then if you look at the cleanest site, the most frequent are pretty close to that level of 5, which actually probably suggests that the soil isn't very alkaline. So there aren't massive emissions, but there isn't much to clean it up. But you can see overall, this histogram has definitely shifted to the right as compared to your more polluted sites. And Skakuza, as expected, is sort of in the middle because it has a mixture of both, anthropogenic emissions as well as being fairly far away from the emissions. So what does it matter if you have increased acid? I mean, I showed you the statue, but let's say we don't care about statues. Well, acidification actually has a really big impact on receiving environments. Primarily impacts aquatic environments, and so that's directly because it actually lowers the pH of the lake or the stream or whatever it is. But it also has an indirect effect because it leads to changes in the metal chemistry. So for example, aluminum is something that at a normal pH of a lake is bound up in some complex and doesn't actually impact any of the organisms. But if you lower the pH of the lake or the river, that aluminum leaches out and it becomes toxic to the organisms that have it. Some soil types can help. So if you have a really alkaline soil, it might help buffer some of the acid, but that's very regional. So the impact of acid rain is not just about the pH of the rain, but the receiving ecosystem, which I've said before. There are some acidic lakes, particularly in Europe, that just don't have fish anymore. They've had too much acidic rain for too long, and now they're officially considered dead lakes. And the thing to remember, if you look over here at this table, so this is critical pH levels for various organisms. So it's fine maybe if you can survive the low pH. So let's say you're a bass fish, and you can survive at a pH of 5.5. But you better hope whatever you eat can survive too, right? So if your food source can't survive, then you're going to be in trouble. And so different species are impacted at different pH levels, but this has a fairly big ecological impact. The other thing in addition to the acidity itself causing a problem, the actual composition, the fact that there's increased nitrogen and increased sulfur in the deposition is a problem for receiving lakes. And in this case, it's actually the nitrogen component that's the biggest problem. If any of you are gardeners, you'll know that nitrogen is a really good fertilizer. But at some point, if you put too much nitrogen on the system from your nitric acid, you're going to end up leading to big blooms of algae. And if you guys have ever seen a really ugly lake covered with green scum, that's what it is. And what happens is all of that algae is consumed, and then the bacteria start to decompose it, and the bacteria use up oxygen. And so you end up with a lake that just has no oxygen. And if with no oxygen, the fish and the other organisms can't survive. And so that's another way that a lake or a stream can completely die as a result of this deposition. And in terms of thinking about transport of pollutants, of course, this nitrogen in particular can be transported out over the open ocean. And this is something that is an open area of research, and something that my group does a lot of research on, is trying to understand how air pollution nitrogen can impact the open ocean. And it's potentially a big deal, because if we look on the left here is a map, I'm showing you regions where there's a lot of nitrogen pollution coming off the continents and hitting the ocean, and that's where those bright colors are. And then the regions on the right is a map showing parts of the ocean that don't have a lot of nitrogen in the surface ocean. And so what ends up happening is that this nitrogen pollution goes out to the open ocean, and it actually stimulates growth. Just like it stimulates growth of that muck in lakes, it stimulates growth of phytoplankton in the ocean. And this actually leads to more CO2 going into the ocean. And this is potentially a good thing, right? Because CO2 is a greenhouse gas, so we want to get it out of the atmosphere and into the ocean. But it also leads to nitrous oxide emissions, and N2O is a much stronger greenhouse gas than CO2. So this is potentially a big problem. So I just wanted to end on this to give you guys a bit more of a personal note on the kind of research that my group does in looking at the impacts of air pollution on remote ecosystems. So this is the last lecture. Now is a good time to go and do the quiz and get started on that homework assignment.